330 to 530 for whatever reason. Okay, midterm 1, calculators, I was skimming through all the exams. It's difficult.
Yeah, they're pretty
difficult. I mean, so.
But they're also curved really sharply.
Yeah.
What does it mean, curved sharp?
Okay, so like in 7A, the averages.
I'm talking about H7B.
Oh,
yeah.
I don't know about
the midterm for H7B.
Oh, they were.
Yeah, they were difficult.
I would know.
At least the one that I had, right? It's not complete. But she's the binders full of exam. I mean, I don't know like some of the problem, but it's okay. I mean, it's also a lot more, at least like going back in time, a lot more emphasis on ENM. I forgot already. I took this video, so I forgot, like, how many teachers on thermo and how many these on years. But all the exams from like the 80s and the 90s, a lot more emphasis on ENM. Even on midterm 1, there's already ENM in there. So I don't know why. Don't remember anymore. So let's move on. Since we talk about ENM, so let's forget about the midterm for now. If you have any question, come Sunday. So recall from lecture 11, right? In finish my recall lecture with the energy of a uniform sphere of charge. We found this by looking at an energy of the work done to assemble the sphere differentially a little bit at a time from infinity to a configuration like this, and we found the whole thing is 3/5, right? Just remember 3/5, 1 over 4 pi epsilon naught Q over A, where A is the radius of the sphere for uniform charge distribution. And then we move on to the Gauss law, and it's not proven. I don't prove it, and maybe we can prove it during this discussion, but this is a statement, right? And we use it to look at the electric field for the line charge. And we establish that the electric field has to be radial. That's the only direction possible. The rest will violet something. I don't know what you're looking at again. And then we found that the electric field, I didn't really complete, I was too fast, I didn't really complete the discussion. So let's do a Gauss law on this line of charge. This has a charge density. It's a line charge density. Lambda, so it's in Coulomb per meter, right? So what I do, since I know that the electric field is radial, I construct a Gaussian sphere. Not a Gaussian sphere, a Gaussian surface. It's a cylinder, but also has a top and a bottom surface, right? So the flux through the cylinder part is, so what we have here is A, right, is divided into 3 parts, right? The first 2 parts through the top surface and the bottom surface, they're 0, right? Because the electric field is radial, right? But the surface element TA is normal, right? So you're left with the other part, the part that's on the oblong, right? But the electric field is constant, so you can pull it out of the integral, right? The surface element dA is normal to the oblong, and that just gives you the area of the cylinder, which is 2 pi r L, right? And this whole thing has to be equal to L times lambda over epsilon naught. That's from Gauss law. So we found that the electric field in the radial direction goes the L cancel, goes as lambda over 2 pi epsilon naught. So that's how we end last Wednesday. Make sure you also know how to derive this using Coulomb's law, or not using Coulomb's law, not using Gauss law, just by integrating the differential electric field coming from every single element along the z direction, right? It's actually solved in Purcell. You should go through it. You should know how to do that integral, right? This is fast, and then you'll see the power of Gauss law, right? Because then you can solve the problem instead of one page, you can solve it in 2 lines, okay? And this sort of makes sense if you think about it, right? If the electric field is no longer 1 over r squared, right? It's 1 over r. Because if I'm over here at some point r, away from the line, right? Most of the electric field will come from some segment of this line that is above length r, right? So since electric field goes as 1 over r squared, but the amount of charges goes as r, right? So the electric field is also as 1 over r. Okay? So next application. Okay. Suppose I have in spherical shell of charge. Okay. This spherical shell of charge. So this is my spherical shell and of radius A, and I put charge Q on it uniformly. Okay. This is empty inside. Okay. So the question is find the electric field everywhere. Field inside and outside. First of all, notice if this is your problem, right, then the electric field in this case here has to be radial, right? Because there is no other direction to find. Right? Any other direction, right? If you have, if the field is, if suppose you have a tangential field, right? Then why that direction and why not, direction like this? Right? The only direction possible that you need right? Once you establish that, by exploiting symmetry, then you can always use Gauss law. Right? That's the power of Gauss law. So from Gauss law, okay, charge inside. Okay. To find the electric field inside the sphere, I just have to construct a mathematical shell, a mathematical surface here of radius r. Okay, the surface S. Okay. And I look at the surface integral of E dot A, the flux through that surface, right? But the flux through that surface, the electric field is normal to the, not normal, it's actually parallel to the differential surface vector, right? Therefore, E dot dA is just E dA. Right? In the radial direction, right? So,
is it Q enclosed in that form?
yeah, charge Q.
Oh, I see. So
Yeah,
that's
charge is, I should have written it as rho. Yeah, something right inside. Okay. So ERTA, right? But then I can pull the E out because also the electric field over here, right? It's going to be the same everywhere along the surface of S by symmetry, right? So I can pull the ER out, right? And I have an integral of dA, right? But this integral is just 4 pi r squared, right? Okay? Okay, but maybe this is much good about nothing, but now looking for the electric field inside R less than A, right? Because the charge inside is equal to 0. Right? There's no charge inside. Inside this mathematical sphere S, there is no charge. Right? Therefore, the electric field is 0 inside. Okay? This is actually a very powerful statement, right? Newton spent a long time, I don't know how many years, because he didn't know anything about Gauss law, to prove that if inside a spherical shell like this of mass m, right, the field inside, the gravitational force inside is always 0. Right? And you can use calculus to prove that. It's very involved. I encourage you to try to do the same. It's actually doable, but a lot of calculus, right? But you see, it's just one line from Gauss law. And how about the electric field for R with an A? Same thing, right? The left-hand side is the flux. I have R times 4 pi R squared, right? But on that side, on the right-hand side, it's just 1 over epsilon naught times Q, right? Okay? Let's define surface charge density. This will be very useful. Right, sigma. Right? Sigma has a unit of coulomb per meter squared, right? Just charge per unit area. In this case here, sigma is just Q over 4 pi A squared, right? Okay, so the electric field here becomes 1 over 4 pi epsilon naught, okay, Q over R squared. Okay, I want to write it in terms of the surface charge density. I mean, this is already the final answer, right? This is the correct answer. Okay. So if I plot the electric field as a function of R, right, it's 0 all the way to A, right, because of that. Right, and suddenly there is a jump, right? So this here is A minus, this is A plus. And suddenly at this epsilon greater than A, right, then you have a field that goes as 1 over R squared. Okay. Here it's just 4 pi Q over 1 over 4 pi epsilon naught. Okay. So this is this one. Okay, because here I have my charge concentrated in a surface area of 0 thickness, right? That's the reason we have that. Okay, so let's rewrite this in terms of the surface charge density. And what you get is the R, when you do the math right, you get 1 over 4 pi epsilon naught. Q is a sigma 4 pi A squared over R squared. The 4 pi cancel. So you have the sigma is over epsilon naught. Okay. And at R equal to A plus means it's slightly larger than A, then E is equal to sigma over epsilon. Is this clear? Okay. Next, another example. Question so far is all pretty simple.
What did you mean by A, R equals A plus?
I mean, because there is a discontinuity here, right? I mean, the field is not exact. This is just a mathematical exercise here. The field is not exactly there is no such thing as an infinitely thin surface charge density. Like physically, things always have a spread, right? But here we are describing a situation where the charges are concentrated infinitely thinly on the surface of the shell, right? So there is a discontinuity here. Right? So the field is not exactly defined at A, right? Well, is it 0 or is it Q over 4 pi epsilon naught A squared, right? So I just say A plus and A minus. Questions so far? You guys have been quiet lately compared to before. Is it because it's more difficult? Or you don't want to disrupt the flow? Okay. Another example. Suppose I want to find field inside and outside of, so instead of a spherical shell of charge, I have a uniform sphere of charge distribution rho is equal to Q over 4 pi over 3 AQ, right? So, of some radius A, it's uniform, it's a sphere, it doesn't look like a sphere, but it is. So, same thing here, right? In this problem, also by symmetry, the only direction that's unique is radial. The only possible direction for electric field is radial. Okay? So the left-hand side is the same exactly from example number 2, right? If I construct a mathematical surface S here, right? Same thing here, I didn't draw it, but well, you get the idea of this one, right? This is A, this is R, right? When R is greater than A, but when it's inside, or if it's outside, then it's over here. Okay. So look at the surface inside to find the electric field for R less than A. The left-hand side still gives you the same, right? Which is ER times 4 pi R squared, right? That's just the flux through the closed surface, right? And it's 1 over epsilon naught times the charge inside the surface S. But that's no longer 0 in this case, right? Because we have a uniform charge density rho, right? The charge inside then is just rho times the volume, right? Times volume. And the volume is 4 pi R cubed. Okay? So the electric field for R less than A then becomes the 4 pi cancel here, then you have rho over 3 epsilon naught R. Okay? Is it clear so far? Okay. How about for R greater than A? Say it again. Oh, see, ER times, this is the flux part, right? The flux over the closed surface is the electric field times the area, right? There is a 3 here. No, I'm still expressing as rho. Right? This is the density. Right? The density is Q charge, the total charge that you spread uniformly across the sphere of radius A. Right? And that's rho. And I'm trying to find the volume, the total charge that is inside the mathematical surface here, the mathematical closed surface, the Gaussian surface S.
So the sphere is an empty.
No, it's not empty. It's a uniform sphere of charge distribution, bro. So the charge is uniformly distributed. Okay? Just like how we built an electron or a positron on Wednesday, right? Imagine creating all this from infinity and forming a sphere of charge Q. Right? So it's uniform. Right? So the first example number 2 is actually just a shell. The charge is on the surface of the shell. So I'm still expressing things in terms of rho, so there's a 3 here. Right, so it's rho over 3 epsilon naught r. For r greater than a, then it's very simple, because then the left hand side again is er 4 pi r squared. The right hand side is 1 over epsilon naught. Total charge inside, right? So it's just q over r squared. No, why is that an r squared? It's just q. Right? So the electric field here is just 1 over 4 pi epsilon naught q over r squared. And just to be consistent with the result from over there, you can re-express q in terms of rho, and then you get some answer. I don't remember as yet what it is, but if you look at the graph of the electric field, the radial electric field as a function of r, what you have is at the beginning is linear, right? Up to radius a, this is linear in r, right? And it's given by that equation. So over here, it's just rho a over 3 epsilon naught, right? And then outside r is greater than a, it goes down like that. This one for r, right? Okay. So that means here what I have is it becomes rho a cube over epsilon naught 3 r squared. Is that right?
Yeah, should it be squared on the...
Oh, sorry, yes, this is r squared. Okay, so there is no discontinuity here in the electric field, but there is a change in the slope. Okay, and I mean you don't have to know all that. You can just substitute for q equal to 4 pi over 3 rho times a cube, and then you'll get this. Okay, and the field goes as 1 over r squared here. Any questions so far? Yes,
Do you know why there was a discontinuity for the other one?
Yes, it's a good question. What happened here, I mean, in reality, there is, in the physical reality, there is no discontinuity, right? Because charge is never concentrated to a zero thickness. But in this case, since this is a mathematical idealization, I'm putting all the charges at that, differentially thin spherical shell. And when you do that, you get that discontinuity. Sorry?
That's when R is greater than A.
When r is greater than a, the field goes as 1 over r squared like that, right? But inside, it's actually 0. All this will become clear in the third example. Actually, today I have time. Let's talk about the next example, or maybe I don't. Any questions so far? Is this all simple and straightforward? Make sure that you know what's happening. But let's move on first, and then we'll come back to this question. Let me erase this part. So we talked about something with cylindrical symmetry. We have that's example number 1 for the infinite line charge, and then example number 2 and 3, we talk about something with a spherical symmetry, right? Or a spherical shell and then a uniform sphere. Third example is example number 4. This is all discussed in the book, by the way. I'm just copying the book. If I have an infinite slab, infinite sheet, of charge distribution, so this looks like a sheet, I suppose. It goes all the way to infinity, infinity, right? Hopefully it looks like a sheet. And has a charge distribution sigma. It's a surface charge. Okay, so again, it's a mathematical representation. This sheet is infinitely thin. Okay, so I can define a surface charge density. Sigma is equal to Q. Well, I guess I cannot really divide by because it's infinite, right? But anyway, sigma has a unit of Coulomb per meter squared, right? And it's a uniform cross, like that. Okay, so let me draw a projection perspective from along the one of the y-axis, say, right? So things looks like this, right? Minus infinity to infinity. Okay. Now, here the only direction defined. Okay, what is the direction? The only unit direction here, the normal. Right? The only unit direction is normal. This is normal. So normal. Correspondingly, on the other side is also normal. Yeah, right? By mirror symmetry. Right? There is a mirror symmetry. So if I like to point in that direction over here, right? It has to point in this direction by mirror symmetry. And there is no other direction possible, right? No other direction is unique. Right? And in any of this we can elaborate, because another thing that we know that would help you is the other integral, right? This other integral that we will actually exploit more in chapter 2. Symmetry is shows that the only possible electric field is normal, right? So when I do that, when I have that, then you can construct, again, a Gaussian field. Box, right? So it looks like this. It's actually a cylinder. Okay? And then the length of the pillbox is 2r, right? So it's r here and it's r here, right? Okay. Then this so the electric field at some distance r away from the sheet, right? We want to calculate that, right? From Gauss law over the Gaussian field box. Right? We find that there are 3 parts here, right? There are 3 surfaces, right? On the, what do you call this, on the wall of the pillbox, right? So the wall this integral of E is 0, right? Because the electric field, again, just like the situation with the which one? The example number 1, electric field is pointing in this direction. Your normal is in that direction, and they are orthogonal, so the dot product is 0, right? A is 0 everywhere, right? But along the wall of the field box, along the top surface, along the wall is 0. Right? Along the top surface, you have integral EA, and that's just E normal times the area, right? The area of the area here, which is whatever you want, right? It's a circle. The other surface again is the same, right? By symmetry is the same. En dA is also En times N, right? And then this integral has to be equal to the 1 over epsilon naught and the charge inside, right? What's the charge inside?
Sigma times A.
Yes. Sigma times A. Okay? We solve that, the 2En A is equal to 1 over epsilon naught sigma times A, the A cancel, then you have an En is equal to sigma over 2 epsilon naught normal to the surface, right? So if you look at it here, this is the sheet. All the way to infinity here, En, and there's also En here. But they're the same everywhere, right? Notice that it's independent of distance from sheet. Okay? And this kind of makes sense because if this is distance r, then the only charge that matter, kind of order of magnitude wise, the charges that matter to the contributed electric field at point r comes from a disk of radius r squared, right? Field goes down as 1 over r squared, but the charge over here goes as r squared, they cancel, right? So the electric field is independent of this distance r. I guess r is quite bad notation to z maybe, right? If you call this that's z direction. Okay, is clear so far? Too simple, too easy. Yeah. Okay. Since we're going to go, so you all know this already, or shall I go through this more carefully? I don't know. See, I don't know what's the.
Could you go there more carefully?
Say it again.
Could you go there more carefully?
Go over which part?
Just in general. Or no, like as you're doing the next example.
Okay. Okay. So okay, this is clear, right? Now, this doesn't have to be an idealization, right? Notice that on this problem here, I can make the Gaussian field to be as thin as I want. Right? This Gaussian field of length C, say, or C naught, right? Thickness. I can make this as thin as possible. Right? Then the contribution of the flux along that wall is 0. The contribution of that flux, A, right, along the wall also equals 0, right? If I make it Gaussian integration, right? So then what I have is just the integral, the surface integral of E plus, say E plus is in this direction, right? Times dA, right? Plus the other condition from the other side of the field. Again, normal is in that direction. So this is G minus. Okay. G minus times dA, right? Has to be equal to, again, it's a sigma times A, right? Again, if I assume that this has a surface, some kind of a surface charge density that's uniform across, right? Then it's a sigma times A divided by epsilon. Basically, I'm saying is that result is not just a mathematical aggregation. I can consider a pillbox very close to a surface, right? The surface doesn't have to be flat. It can be any surface, right? As long as I can construct my Gaussian field within enough. Then small, right? And this is always true. Okay? There's always some kind of a discontinuity. The electric field is pointing in this direction on one side of the surface, and is pointing in the other direction for the other side of the surface, right? Okay. Just to be more consistent, I don't like writing electric field, defining the direction separately, right? So I can write this with a convention that E minus is in this direction, and I have an integral of E plus dA plus an integral of E minus dA has to be equal to sigma A over epsilon naught. Okay. So then in that case, again, if we assume that the field is actually small enough, right, then this I can pull the electric field out of the integral, right? I assume there's not much variation in the electric field across the Gaussian field, right? Then I have E plus minus E minus, okay, times the area, okay, is equal to sigma area over epsilon. Okay? So E plus minus E minus is equal to, they cancel, sigma over epsilon. Because any surface, as long as you have, this is back to your question again, right? As long as I have an infinitely thin sheet of charge, right? Then the electric field outside minus the electric field inside has to be given by sigma over epsilon. Is this clear? And I don't need to know exactly the composition of the thing. It doesn't have to be an infinitely thin charge, right? If I have something like this, right? And there's some kind of a distribution. Okay. All I'm saying is that maybe I don't want to worry so much about distribution here. If this is actually small enough and this is long enough, then the electric field here, or the electric field outside minus the electric field inside, has a discontinuity that's given by that, where sigma here is just the density times dx, where this thickness is dx. Okay, or I can, just to be more careful, I can also integrate from x1 to
Why is it minus? The E plus minus minus?
Oh, because I'm defining the direction of the electric field to be all pointing in the same direction. So you can imagine in this case, and we'll see on an example later on, right? Suppose if I have a line sheet of charge, right? Here you have a E normal. Over here you have another E normal over here, right? And then the discontinuity, right? En is just sigma over epsilon naught, right? Okay, because En is sigma over 2 epsilon naught. Okay? But you can also imagine I put a chart, I put another, I don't know, I mean another slab here or something. I have another charge Q here, right? It also adds its own electric field. Okay? Right? And since by principle of superposition, then all the electric field has to add, right? So across here, say if I just look at this point, there is a discontinuity, right? The electric field doesn't have to be positive and negative, right? All it has to do is that it has to have a difference, and the difference has to be given by that. You see my point? People are confused now.
I guess it's kind of confusing because they don't cancel out. I mean, they add up rather.
Yeah, one of them is on one side of the surface, the other one is on the other side,
Yeah.
right? And there is a discontinuity in the electric field. One points that way, and one on the other side points the other way. The factorial difference is sigma over epsilon naught, right? It's a factorial difference, right? And it doesn't have to be, sigma over 2 epsilon naught, sigma over 2 epsilon naught. What you could have is something like this. Some number E plus sigma over 2 epsilon naught. And over here you have some number E minus sigma over 2 epsilon naught, right? And so you have a small e here and a big E here. Across any surface density, there is always a discontinuity in the electric field. That's the lesson here that I want to emphasize. Okay. Anytime you have a surface charge density, above and below, there is a discontinuity of this much, sigma over epsilon. Okay? Let's go back to that example, the original example, the first example that we did, right? Spherical shell. I'm going to draw a field of radius A, right? And charge Q uniform. Uniform across, right? And then sigma is just Q over 4 pi E squared, right? Okay. And remember, what's the charge inside? Yeah. What's the charge outside?
The electric field of the charge.
Sorry, yeah. What's the electric field outside? 1 over 4 pi epsilon naught Q over R squared, right? And you have to you can start with this for now, right? And then you actually if you do the math right, you realize that the electric field. What did I write down as the electric field? What is this equal to? It's in the note somewhere.
Oh, in terms of sigma?
Oh,
Yeah, in terms of
A
sigma.
squared
What was that? I
sigma.
forgot.
A squared sigma over epsilon 0 r squared.
E squared, no. Sigma
Or
A
sigma.
squared over 4 pi epsilon naught R squared, right?
Yeah.
Yeah.
No,
No, there wasn't a 4 pi.
Yeah, the
Q
4
right.
pi isn't canceling.
Yeah, there's no 4 pi. It's just ER
Sigma A squared
over
R
epsilon 0.
cubed, right?
No, r squared, but no 4 pi.
No 4 pi. Yeah, no 4 pi, correct. Epsilon naught
Yeah, the sigma.
R squared. Okay, this is right, huh? Okay, so the electric field at R equal to A plus, right? The electric field is just sigma over at radius exactly equal to A slightly larger, the electric field is the A cancel the R squared here, then you have sigma over epsilon naught. So at the surface, E is equal to sigma over epsilon. You can think of the Gaussian pillbox here if I want. Right? And then you can analyze things in terms of the Gaussian pillbox. Right? If this radius A is large enough, or you make the pillbox thin enough, this looks like a flat sheet of charge, right? And then you have E is 0 here, and then E is sigma over epsilon naught, right? Outside. And the discontinuity, delta E, across the surface is given by just that, right? Sigma over epsilon naught minus 0. Okay? So that's when you have a sphere, right? It's the result is different. Globally it's different from an infinite sheet. In an infinite sheet, you have sigma over 2 epsilon naught outside and sigma over 2 epsilon naught here on the other side, right? Because they have a symmetry. Here you don't have that kind of symmetry because the whole thing is bent into a sphere, right? So the electric field is 0 inside, but you still maintain this kind of difference across the surface. Okay, is that clear? Question? I think we should stop here. So the next topic I want to actually find the energy to build a spherical shell of charges. That's next.